For those of you who haven't met me, greetings from the garden spot of Southwest Ohio, where I work out of my home on behalf of the aviation industry. And I'm not necessarily going to be sharing like a whole lot of philosophic stuff about why we're doing that, why we're interested in sustainable aviation fuels. I'll touch on that clearly, but Elise asked me to focus, on three questions. Why the CAFE interest? Some of you who might be new to the project are thinking, okay, Waiuli, Southwest region, rubber production, resin, what the heck? Why aviation fuel? So I'll touch on that a bit. So why the CAFE interest, and then what are the tangible outcomes from SBAR that will facilitate CAFE's future progress, and how SBAR research is setting the stage for future research and development that will promote CAFE goals. That's really how I'm focused. I hope you appreciate or enjoy the approach that I'm going to use to do that. So cover page here, for those of you who don't know, and I've brought this up in previous SBAR sessions asking people to raise their hands if they've flown through LAX in the last 4 years. But if you have, you've had some minuscule amount of renewable jet fuel on board the airplane, even though you didn't know it. Fuel has been being delivered to the Los Angeles International Fuel Farm since March 10th of 2016. That fuel is basically contracted by United Airlines from a refinery just outside of LA called World Energy Paramount. And that fuel is produced primarily from beef tallow. But there's a lot of other methodologies whereby sustainable aviation fuel can be produced from both thermochemical and biochemical processes. And I think John's going to touch on a few of those things. So next slide. So a little bit about CAFE. CAFE actually is a public-private partnership. We have 4 primary sponsors, 3 on the commercial side, 1 on the public side. The public side, it's the Federal Aviation Administration. On the commercial side, it is Airlines for America, the trade group that represents airlines in North America. The Aerospace Industries Association, which represents all of the manufacturers of aircraft equipment, and the Airports Council International, basically where the point from which we provide our service. And it's oftentimes where the airline winds up being the focal point of industry's interest in what's happening with respect to aviation and environmental issues. Anyway, CAFE was stood up in 2006 to facilitate the introduction of sustainable aviation fuel, because even that long ago, 14 years ago now, the industry represented that we were doing pretty well with technology that addressed other environmental issues like tailpipe emissions and noise, but we didn't really have an overall approach on reducing greenhouse gases. So this was in the period where things were going hot and heavy with the Kyoto Protocol, and those of you who are younger probably have not even heard of that, but the Kyoto Protocol was one of the precursors to the Paris Agreement, which was intended to try to get the world to focus on reducing greenhouse gases. So we've been in place since then. We had done work back in the 80s and 90s following the first oil shock to know that we could produce synthetic fuels that met all of our requirements. And so this basically was just a kickoff of a more concerted effort to foster the development and commercialization of alternative fuels. And what's important to us in the aviation industry is we're interested in a drop-in jet fuel. Nobody can actually afford the cost associated with forcing our fleets to use different fuels. Several $1 trillion investment in the existing commercial fleet that's out there, nor as well the infrastructure changes that would be required to switch fuels, like to go to hydrogen or some other unique type of fuel, liquefied natural gas, et cetera. So we've endeavored on this approach for drop-in jet fuels. They deliver the safety and performance that we demand. Our hope is that we get them at comparable cost. They deliver the environmental improvement that we're after. And in addition to the environmental side, we're also interested in securing the energy supply for the aviation industry. And this issue is important on the commercial side, but it's even more important on the military side. Next slide. So in the 2008 timeframe, just a couple years after CAFE got formed, the industry got together and got more specific with respect to voluntary commitments the entire aviation industry made to the world to say, we are going to continue to improve efficiency on an annual basis. That's goal 1 on this chart. Goal 2 is that we will actually freeze or cap our net carbon emissions from 2020 onward, and we will seek to achieve a 50% reduction in net emissions by 2050 from 2005 levels. And we further announced that we will attempt to do those things through several pillars of work. The introduction of technology, including sustainable aviation fuels, and the improvements of operations and infrastructure. And we also said at that time, and guess what? We're serious about this, and we're willing to submit ourselves to a carbon-based, a carbon trading mechanism from that 2020 time period onward, such that if we can't develop sustainable aviation fuels significantly quickly, we will offset our emissions through the use of offsets. And so that goal 2 there is currently being implemented by the International Civil Aviation Organization. That's a UN body that covers regulation of environmental impact for the aviation industry. That program is called CORSIA, Carbon Offsetting and Reduction Scheme for International Aviation. That it will be implemented at the end of this year. So going forward from next year onward, if an airline exceeds their emissions from the 2019 baseline period, they either have to offset those emissions or reduce their offsetting obligation through the use of sustainable aviation fuels. Next slide. So for your continuing education credits, or your ongoing education credits, just a couple comments with respect to the technical details of jet fuel from both a use and chemistry perspective. Jet fuel is typically referred to as Jet A. It's kerosene, a middle distillate fuel product that comes out of existing petroleum refineries. And it's got a specification associated with it, ASTM D1655 over on the right-hand side. It's basically a pure hydrocarbon or a mixture of pure hydrocarbon components. And it's important that we talk about the certification basis or the details of that, that specification, because all of the safety and performance characteristics of the aviation enterprise are predicated on the ability for the engine to operate off of a certain fuel type and the ability of that engine to guarantee the performance of the aircraft under all sorts of circumstances. The thing that's unique about jet fuel is that we don't just use it for combustion in a combustor, and that's what a modern combustor looks like there in the middle of the page. Fuel comes in through the fuel injectors around the outside, come into a fuel nozzle. That nozzle sprays fuel out into that sort of elliptical shaped portion in the middle, and extremely hot, energetic gas blasts out the back end of this combustor and runs through the turbines. Before we burn that fuel, we actually use it in a whole bunch of ways inside the aircraft and engine as a coolant, as a lubricant, a hydraulic fluid, a ballast fluid, serves as a swelling agent, a capacitance agent, et cetera. And then finally, we inject it into the combustor to generate heat or turn chemical energy into gas horsepower. So This is, it's a sophisticated, complicated life associated with the combustion of fuels. We're after high energy content on a volumetric and mass basis. We're after very stable fuel that has a high flash point so that we don't have explosions when, we're fueling aircraft on the ground. That's a good thing. Very low freeze point because when you're cruising at altitude, if you're not aware, take a look at the flight following monitor on your next flight and see what some of the temperatures are that you encounter at 40,000 feet. Very cold operating environment. So we can't afford for that fuel to freeze in the tanks when you're cruising. So a bunch of characteristics like that. So turbine fuel is used for multiple purposes and its creation has to be carefully controlled. Next slide. So what is it specifically? It's this mixture of hydrocarbons, as I said, normal and branched paraffins. Those are those zigzaggy chains that I have there shown directly to the right of that wording. Normal is the straight zigzaggy one. The branched ones have hydrocarbons coming off the sides of the chains. Then we also have mono, di, and tricycloparaffins. That's where those chains close in on one another and form different types of loops. And then as well as mono and dinuclear aromatics. So these are basically 4 different types of molecules. They come in normal distributions of carbon ranging from C7 to C17. And the GC by GC diagram on the right-hand side gives you some perspective on actually the number of molecule types that you find in jet fuel. And it actually can range in a count of several thousand, depending on the refinery that it comes for. So we don't have a standard formula for jet fuel. We just know that hydrocarbons in this range give us all the properties that we ask for in the ASTM 1655 specification that we have on the previous page. So again, what we're interested in is creating this kind of fuel synthetically that allows us, when we burn this fuel, to actually reduce net greenhouse gases. Next page. So what are we doing with sustainable aviation fuel? Again, repeating, we're still after aviation fuel because it maintains the certification basis of the entire fleet and the entire way that we operate aircraft. We're interested in those fuels becoming more sustainable, taking things like social, economic, and environmental progress into account, but especially addressing the greenhouse gas reduction. And how are we doing that? By creating synthetic jet fuel with biochemical and thermochemical processes. So recreating in whole or in part those molecule types that I showed on the last page that deliver the characteristics that we need. Next page. So how are we doing? Well, on the technical side, we know how to make these fuels. We already, over the last several years, we have approved as an industry the production of synthetic fuel from 7 different processes so far. There's another 4 that are in process that can get approved over the next 12 to 18 months. And then there's about at least another 15 in the pipeline, and every couple of months a new one comes out. So it's really encouraging from my perspective that there continues to be a lot of focus on the thermochemical and biochemical processes to produce these hydrocarbons. We also know that we can use all of the major sustainable feedstocks that nature hands us, that being in the form of either lipids, sugars, lignocellulose directly, or various hydrogen and carbon sources, which could be different waste streams from a circular bioeconomy, emissions off of other industrial processes, etc. We produce them synthetically through those methodologies. And then because in many cases, these synthetic processes don't give us every molecule that we're interested in, we blend them with conventional jet fuel. And after we do that, these fuels are identical to jet fuel. They're indistinguishable, actually. So they can be dropped into the existing fuel system and can be used any way that jet fuel is today. We know that with some future pathways, we'll be able to reduce our blending requirements. And in fact, we already have one fuel right now that we know can be used at 100% without blending. But we're a conservative industry, and that'll come in a couple of years likely. And we continue to do things to streamline fuel qualification, reducing the time, the dollars, and the methodologies associated with doing that. Next page. So technically we're doing well. How are we doing commercially? Well, we got 4 years of sustained use, as I indicated. The red bars on the right here show our trend in usage over the last 4 years. An increasing trend. Looks like we'll take a pretty good leap this year if we duplicate the production in the second half that we had in the first. We have one and a partial facility operating here in the US. There's another one operating in Finland. There are several additional facilities under construction here in the US. 2 of those are expected to come online prior to mid-year next year. There's still a cost delta that's a challenge associated with these fuels. In some cases, that cost delta can be closed with policy, but not in every case. So in spite of that, we still have $6 billion of airline offtake commitments for in excess of 350 million gallons per year of jet fuel production. Next slide. And here's an example of what we believe the next 10 or so facilities are. I'm personally aware of other things that are happening in this time frame, but haven't been publicly announced. And you'll see some more announcements actually made over the next couple of months in that regard. But you can see that we may, knock on wood, get to around the billion-gallon level in the 2025-2026 timeframe. Next page. How does that compare to what we've seen from other fuels? It's not a whole lot different. The early years are always tough. You can see the trends there for biodiesel, for renewable diesel, and where we're at right now with sustainable aviation fuel. What we know, though, is that policy can change this picture overnight, and that's clearly what's going on now with renewable diesel, with the inclusion of policy from the RFS, federal tax treatment, and the state policy through the California and Oregon low carbon fuel standards as an example. So not too different than what we've seen with the other fuels, and you probably all know that ethanol for gasoline blending is also already at the 15 billion gallon level, more or less. Next page. So in summary, SAF are key for meeting the industry's commitments. There's a whole bunch of folks working with us to foster, catalyze, enable, et cetera. There's technology readiness level or fuel readiness level activities from 1 to 9. John's working with folks that are closer to the 1 end. I'm working with folks that are closer to the 9 end. We know we'll be able to get to fully synthetic fuels at some point. We've got facilities online. The real challenge, though, is commercial viability, and hence our interest in this project. Our potential to accelerate the use of SAF is a function of addressing that commercial viability, and then things like engagement, continuing to foster offtake agreements, the replication of first facilities, additional technologies, et cetera. Next slide. So why the CAFE interest? In a word, hit return. It's bagasse. And a couple people have used this. This is a great picture Bridgestone has offered up earlier on. Right there after the natural rubber, to a lesser degree after the resin, to a lesser degree the bagasse. You can hit the build again. But from my perspective, from an aviation perspective, and resonating Trump here a little bit, right? This is beautiful, bone dry, finely chopped, continuously produced, aggregated, sustainable lignocellulosic co-product stream that's potentially ready for the bioproduct reactor as a prime or mixed feedstock. That's why the CAFE interest. So although I'm very interested in high quality rubbers for the aviation industry, because we do demand a high quality rubber in a fair quantity, from this project's perspective, I'm very interested in understanding whether bagasse helps close the business case whether it can be produced at a price that's affordable to go into a refinery. And then the last slide, the other two questions. So what are the tangible outcomes from SBAR that will facilitate CAFE future progress? Well, you highlighted that yesterday afternoon in spades. Research that validates the full supply chain value proposition of Waiuli for sustainable production of rubber, resin, and bagasse, and the valorizable co-products that come out of that. And it's everything that the project is doing is required to get to that valorization, from breeding to agronomy, processing, co-product development, et cetera. So very pertinent. How is SBAR research setting the stage for future research and development? I'm a strong advocate for the NIFA CAP kinds of projects. That's how I became engaged with Kim and why she reached out to me in the first place to participate on this project. But we have seen in the past that these types of projects can produce phenomenal results in this integrated approach, with the commercialization entity being backed up by significant research. So it's only when research enables true optimization and delivering decision support tools, for instance, that will allow Bridgestone to decide to move forward with commercialization. And if they do that, we'll have a shot at bagasse-derived co-products. So CAFE and others believe that coordinated agricultural research projects are one of the best ways to jumpstart new use agriculture. We appreciate what you're doing. Please continue your vital efforts. I'm very encouraged by what I continue to see. We've got challenges in front of us. I recognize 10 cents a kilogram is a high price compared to other lignocellulose that's available for some of the projects in the Southeast. But I'm interested in seeing us continue to hammer away at this issue to enable Bridgestone to meet their goals and to make this bagasse available. Thanks.
And Steve, you got a bunch of questions in the chat, about 5 or 6. I don't know how much time we have, but Bob White just posted.
Yeah, I think we should take the time for a few of these. So
great.
Go ahead.
Yeah, so Bob White just posted, what do you believe is the top conversion process for bagasse to jet fuels?
That's, yeah, Bob, it'd be great if we had the detailed answer to that one, right? So the issue is that there's this trade in CapEx and OpEx across all of the conversion processes. And just so as an example, right, we know that today hydroprocessing of esters and fatty acids is about the most cost-efficient approach for producing fuel. Very low CapEx, but the OpEx is higher than we would like it to be because, as an example, right, with the most used feedstock for fuel production actually happens to be soy oil. And if you compare the price of raw soy oil on a $1 per gallon basis, it's already higher than the price of jet fuel by itself. So you've got that at one end, and perhaps at the other end, we already have maybe the other end of the spectrum, which is with Fischer-Tropsch conversion, the potential for a pretty high CapEx, but a modest OpEx, especially if we're using waste resources, like in the case of MSW, where the feedstock can come with negative cost. And then you've got these multiple processes in between. So I don't know that I can give you an answer on this. I think we've seen different scenarios where we take into account realistic prices for feedstock. And, some of those technologies kind of fall on top of one another. But the good news is that there are multiple approaches with respect to using lignocellulose. So, and there's even a couple more very interesting ones that are coming along that haven't had a lot of focus put on them yet, like, for instance, Shell's IH² process, and then even additional work that GTI is doing with that technology in a process called CoolGTL as an example. And then you got somewhere in between, HTL technology is a possibility. So I think it really does depend on the specifics of what's being proposed and whether there are some integration techniques that can be used to to make one be more successful than the other. But I do happen to be an engineer, and I believe in engineering processes. Biological processes scare me a little bit. So I would tend to gravitate in the direction of thermochem processes. But I understand the challenge associated with doing that. And we've got, Lonza in their approach of producing fuel molecules through biochem processes and then upgrading to jet fuels, which may make perfect sense too. So I haven't given you a great answer other than to say the future is bright with respect to opportunities for different types of conversion processes.
Great, thank you, Steve. And Kim had asked, do you think these dates for future use will be pushed back because of COVID? And Colleen kind of tagged on, or because of historic low crude prices?
So I hope that you're all pleasantly surprised to know that the activity over the last 5 months has been pretty robust. On both the airline side as well as producers. We do see a little bit of impact from COVID, with shutdowns and some other stuff with respect to supply chains. So yes, obviously there's going to be some effect. So far, it hasn't been huge. You saw the fuel usage on that early chart. It's actually very high through the first 6 months of the year. And Colleen, you're absolutely correct. Low crude prices are having an impact. But what we're finding is it's the policy that's making the difference, even with low crude prices, that with the appropriate policy, and that's a reflection of societal demands for making aviation greener, that policy can really contribute to commercialization activity. So yeah, we see some delays, a little bit, not much. Things are still going well. Everyone should expect to see significant layoffs from the aviation and aerospace industry starting in the October timeframe. So I do expect that from October for the next 6-8 months, things will be tough with respect to airline engagement, but we got plenty to do on the technology side. And there's a lot of folks in both the Senate and the House who have been seriously reflecting on how they can help the aviation enterprise become greener. And there's actually language put in the CARES Act that would have introduced a blender's tax credit specifically for aviation fuel that would have been a game changer. And so we're still expecting that could be the case with a simple stroke of the pen. So we're just going to keep working on nuts and bolts. Things will happen on the policy side in their own time, and just going to keep hammering away at it.
Okay, so Steve, there's some other things in the chat that maybe you can answer. We're going to move on to John. I think we'll today. So we'll move on to John now. Thanks, Steve.
All right. Well, I give you my greetings from the garden spot of southeastern Washington. I don't know if we're quite as gardeny as where Steve is in Ohio.
Wait,
but
there are no garden spots in southeast Washington.
we irrigate, Steve.
Wine, grapes.
All right, let's go on. I've been asked to talk about the three same questions that Steve spoke about and that we heard about yesterday. So why are we interested in your work? And what are those tangible outcomes? And how will this work help change how P&L, how my organization is looking at R&D? So as I talk about these slides, I'm going to give you a little bit of history about P&L and my work there. And I'd like to give a couple of examples from today's biorefineries and use this to tie both my own work and the work that I see in current biorefineries into what I see going on in SBAR. I would also, Kim, offer to give a much larger presentation if you guys have, if you guys do that later. So this is a slide. I pulled a few slides out of something I gave that was about an hour long. Anyway, let's go on to the next slide. So I'm going to give you this brief history of P&L in biofuels and bioproducts. Next slide. And I'm going to start back when I started. And so this is, you're seeing a history of my work or my interest working with this team at P&L. And back in the early 2000s, we were working on extracting more value from corn fiber. And that should sound familiar to you because you're working on extracting more value from the gas and resins and so forth. Of course, people know that corn fiber is one of those things that comes out of a corn dry mill and is sold in the DDGS piece. But animal feed does not need all that sugar. Corn fiber is rich in hemicellulose. And that's what we were looking to take that hemicellulose and start making products catalytically. And the thing that we were working on was propylene glycol. Wonderful and interesting science that I'll just skip completely in developing these catalysts and so forth. The bottom line was that we were able to commercialize this process. And what was fascinating was we didn't commercialize the process on corn fiber. Instead, we commercialized the process on waste glycerol from biodiesel plants. But the chemistry and what we were doing was all based on this work as we were trying to improve what was going on with corn fiber. And I expect we'll see a lot of the same kind of thing from your work, in which you're doing certain things, but they'll find other applications for that may even be more valuable. Anyway, let's go on to the next slide. I'll move down the road a little bit. You know, it took 10 years from when we started that work on developing the catalytic system to where we actually had it commercial and full-size plant. So we'll move down to 2010. 2010, P&L was working on a new way to produce high-quality jet fuel. And all of the things that we were working on before just required huge amounts of hydrogen gas. And that was something we were really thinking, how can we do something that doesn't take so much gas? And we were working on a number of small alcohols that we were making from thermochemical processes or other processes. In the end, we needed this really inexpensive and good source of the alcohol. And so we partnered with LanzaTech and developed this process in which we take the alcohol and do a dehydration followed by a oligomerization. And the real key here was, again, a catalytic process, and it was control of the branching and the length of the chain, right? Controlling that branching is critical because sometimes we might want to make diesel fuel instead of jet fuel. And if we have too much branching, the diesel fuel is horrid. And we see that with one of the companies that does alcohol to jet. They can't make a diesel fuel because the cetane is so bad. By controlling that branching, we can improve the quality of the jet fuel and make something, if we wanted to go into the diesel range, have a really high quality diesel fuel. If we wanted to make a high RON gasoline, we would be able to do that. So it gives you that kind of flexibility. Long story short, LanzaTech has formed a company called LanzaJet, and we're working on commercializing this now with the first 10 million gallon scale plant being built now, and with 3 additional plants being worked on later. Again, this was made possible because we were working with a low-cost source that could make the ethanol, a waste gas. So in the previous slide, I didn't mention it, but we were working with, again, a waste material. Let's go on to the next example. Today, our focus is on sludge. At least that's one of our focuses. And again, you know, these sludges require high energy to clean and present an environmental issue. And so it's the kind of feedstock that we like because we can solve another problem. And it's in developing some technologies that we can take these sludges to things that are valuable. And it turns out sludges from wastewater treatment and manures make incredible diesel fuel and actually make pretty good jet fuel as well. In fact, having more lignocellulosic in them actually improves the quality of the jet fuel, where we can get jet fuel that has all the different kind of components that Steve spoke about. All right, for interest of time, let me go on. So The other thing that is a big focus of mine is the Bioproducts Institute. This is an institute that PNNL has with Washington State University. And our focus is to look at how can we improve the carbon that needs to stay in the economy, right? Not all carbon needs to stay in the economy. I don't need to be burning coal to make electricity anymore. In fact, I don't know that I really need to be making gasoline in the future. There are other opportunities or other solution sets in electrifying, but there are things that we cannot electrify. Aviation and heavy trucking are examples of that. They become things that are critically important. There's also chemicals and plastics that will always need carbon. So there will always be this need for carbon in the environment. And that's what we want to work on, is where do we need to have these solutions for these carbon sets that need to stay in the environment. What we find is that we need to start thinking about how can we solve another problem? How can we provide an environmental value proposition that can help change what's going on here? All right, we have a bunch of current initiatives that consider wastewater, that's looking at deep decarbonization and a number of other things. Because of time, let's go on. So a brief history about PNNL. The thing I wanted to get from there is we really are focused about solving problems and working with people to get these solutions into commercial practice. And we've learned a lot of lessons from that. And as I've looked at the lessons we've learned and looked at current biorefineries, there's a couple other lessons. So let me go over 3 real quick. The first lesson is structural components are really hard to make fuels from. Okay, so we have this question about bagasse. Look, today we make 18 billion gallons of biofuels in the United States. 97% of those come from starch or vegetable oil. 0.04% of those come from structural components, right? It's hard to make this work. And Steve hit some of those reasons, and a lot of those have to do with capital and just other challenges that they have. All right, so there's one lesson. I'm not saying we can't do it. I'm saying it's difficult and we haven't done it yet. Next slide. If we take a look at where we do make biofuels today, this 18 billion gallons, the thing that is what we see is that they keep things really simple. The capital cost is kept really low, and the operating cost is also, to the best that they can, controlled. They do this, you know, if you take a look at a corn dry mill, there's only one conversion product. There's 3 products that they sell though. Corn oil is an extraction product, and then all the residuals, DTGS. Of course, there's some add-on things where people are trying to add some additional things and get a couple more values, but they're not complex, right? However, they do extract the most value from every process stream that there is. And I see that with your work. I see that you're trying to extract that value, all right? The other thing that we know is separations can be really costly and can kill processes. And I'm pleased to see the work that and the focus that you have on separations. All right, so keep things simple. That's a second lesson. Third lesson. Don't forget about underutilized carbon that's collected, right? For SBAR, you have this carbon source that you collect because you're growing that carbon for a different purpose. In PNL's work, we've been looking at a number of waste streams, municipal solid waste, plastics and resins, sludges, manures, and so forth. I will add that, you know, I mentioned that the vast majority of biofuels are made from starch or lipids. The other 3% is actually waste carbon, right? So this is renewable diesel and renewable natural, I'm sorry, a little bit of renewable diesel and a little bit of, renewable natural gas that come from a number of different waste sources. So carbon that's collected, it's really important that that any time that carbon is collected, that we figure out better things to do with it. All right, so let's go on and let me see if I can just quickly get to these 3 questions then, and my view of SBAR and its value that you're bringing. So next slide. All right, so we need a new biomass supply. We, you know, there's the billion-ton study that I think DOE has finally retired. But if you read the billion-ton study, there's not a billion tons. There's about 400,000 tons. And all of this other material, this additional 650,000 tons to make that billion, comes from purpose-grown crops that nobody makes. So we actually do need to find more carbon. And I think SBAR is really giving some critical data for how can we get some carbon in the Southwest. We know that carbon production, that biofuel production, that biomass is a regional thing. And we really, really critically need this information about the Southwest. And I think what we're learning in the Southwest and so much what you're doing will be helpful with other places, such as where I live, which is also a desert environment. So this biomass resource, I don't think it will ever be cheap enough to have a purpose-grown crop. We need to be thinking about how can we solve another problem. I see that in your model as well. The SBAR model is the biomass is being grown for rubber. And so we now have this, we're now trying to take more advantage of all of the gas and resin and so forth. All right. But it is this solve another problem. In the Bioproducts Institute, we're looking at problems that we're trying to solve have to do with environmental problems. I think the problem that you're trying to solve is how can we make rubber, and you're then keeping a focus on the environmental issues, and I think that's really good. Okay, biorefineries have to be simple. I have really appreciated the talks I heard yesterday and last year. That the focus that you have is you're keeping these transformations limited. You're seeking the most value from each process stream, whether it be the resin or the bagasse, and you're even looking at non-fuel uses of the bagasse. I think that is important because I do think we're going to have to see some things like that before we have some technologies that really are ready for making fuel from them. I will add one more quick thing here. The lignocellulosic processes that are based on thermochemical approaches, we can make some good jet fuel from them, and we can make some very nice jet fuel from them. We also make quite a bit more diesel or gasoline, depending upon what the process is. All right, anyway, what we have found in my own work in commercializing things is that little things can really cause the problem and keep you from being able to commercialize, right? So in that propylene glycol example I gave, the thing that almost kept the process from going commercial wasn't the catalyst life. We had all that kind of stuff figured out. We had a small impurity that we were making that was less than 0.5%, but it just happened to distill at exactly pretty much the same temperature as the main product. And that almost killed the entire process. It's really important that we start thinking about these little things. And these little things that can kill a process are toxicity, the impact of impurities. There's a number of little things like that. And I really appreciate the work that I see that you're doing to make sure you understand toxicity. And I also heard yesterday examples of where people are thinking and talking about the impact of impurities. In that case, they were talking about rubber quality, but I think it's really important, and I'm pleased to see that you're thinking about that. Next slide, please. Got just one more slide, and then the tangible outcomes that I really want to see have to do with sustainability, right? I referred to 1 billion ton this report before. The fact of the matter, if we're really going to make enough biomass to really make a difference, we're going to have some water, land issues and fertilizer issues and things like that we're not dealing with today. You're taking that right on. You're understanding, in the Southwest, we can't make these silly notions that, oh, we just won't use irrigation. Instead, you're taking everything straight on. And I appreciate that you're understanding water, its impact, you're understanding the fertilizer, you're understanding temperature. This is really critical. And I think that kind of information will be able to help us think about other regions as well. I do think that the work that you're doing on social equity is going to become increasingly important. I was thrilled to hear that what you had yesterday. I think that in our COVID state, we're thinking a lot more about social equity, and I guess just not the COVID state, but with other things that have been happening at the same time, we're thinking a lot more about social equity. This is really important about to aviation fuels, by the way, because the zones, airports, people who live around airports tend to not be the nicer homes. And there's real problems around ports and airports and so forth around air quality. And so this is something that we need to think about. I'm glad that you're facing and looking at social equity, and I hope that we can learn more from you on that. Finally, I would like to say that the industry really needs an honest and reliable techno-economic analyses that don't paint the rosy picture, that are not based on nth plant, but look at the real system. And I just want to really caution you as you do your techno-economic analysis to be as honest as you can. I'll just leave it at that. We can talk more later. Okay, last slide. My purpose, the things that I really focus on is how can I develop strategies for deep decarbonization? I can electrify a lot of things. We do a lot of work in my portfolio that I oversee, looking at batteries, looking at the grid and these kind of things. But I need, and we need, a solution set for understanding carbon cycles where electrification is not possible, understanding land and water. And you're facing this and you're doing this, and we can partner now. So here's the very final slide. And one of those things that we would love to do with you right now, next slide, this is the final one, is start looking at some of the materials you have. Start taking a look at some of your materials after you've extracted the value you can. Give it to us. Don't dry it. Don't do anything else. We'll take it in any state we can get it. Get the resins and other materials out that you can, but don't work too hard on getting too much out, because that will even make a better fuel. We have some thermochemical processes that I think your material would be really wonderful to look at. All right, so that's what I wanted to tell you. I think you're doing some great work. I'll talk to you a little bit more this afternoon about some thoughts, and thank you.
Thanks, John.